So far, we've been able to find frequency domain representation, right, for periodic signals, right? Which is achieved by doing the Fourier series, whether it is a trigonometric, right, or compact trigonometric, or the complex exponential. All of these are different ways, but they get you the same thing. They get you a frequency domain representation of your signal. And you can convert from one to the other. You can convert from the format of one to the other easily, okay? So that's what we have been able to do. But then in real life, actually in real life, you cannot have theoretically a periodic signal, right? Because any signal that you will deal with in real life is going to start at one point in time, is going to stop later, right? So you cannot say, theoretically, you cannot say it is periodic. Even a sinusoidal that you use in the lab, you use it at the start of your lab session, at one point you'll switch off the device, right? And at that point, the signal will stop. So this means it doesn't go all the way to infinity, right? So in real life, we don't have the theoretical case of pure theoretical periodic signal, right? We typically deal with aperiodic signals, okay? And if this is the case, okay, what can I do? I cannot look at the frequency domain, or I can look at the frequency domain. And if I need to look at the frequency domain, how can I do it, right? So rather than giving you the theory directly, which is just an expression, right, I will first tell you why this is the case, why there is a way, and how does it relate to the periodic case. And then from there, we will move to the expression. In the book, you will find kind of a mathematical proof. It's just for your readings. So you don't need to do the mathematical proof. I'm not going to ask you to prove the aperiodic case from the periodic case, but I'm going to explain to you how they are related right now in kind of an experimental qualitative manner rather than a mathematical derivation manner, okay? So again, you can read the proof just to expand your understanding of the topic, but you are not required to do that proof, okay? And if you don't want to read it, don't read it, okay? So basically, let's go back to the example that we have solved in the class. Remember this example? I've just showed it to you also a few minutes ago, right? The example of the square function, right? And we said that it will have a duration tau, right? And it will have a period equal to t. So it will have a period equal to capital T, right? And then it will repeat again. Okay. So the same thing is going to repeat over and over and over again. Okay, so another square, and then after a duration capital T, another square, and so on, okay? And all the squares are with the same width tau, okay? Remember how we found the exponential Fourier series coefficient for this one? How did we find it? Not the expression. How did we find that expression? Applying the rule directly. What was the expression? dn is equal, so this is my f of t, right? And dn, in this case, was equal to 1 over the period. So let's call this t naught so that we are... so 1 over the period, and then you integrate over one period. What do you integrate? F of t, right, the time domain signal, and then multiplied by exponential of, okay, j or minus j? Minus j n omega naught t, right? And you integrate with respect to the time domain, right? The time variable, okay? Now, we solved this for two cases. The case that n is equal to 0, right? Because in that case, the whole exponential disappears, right? This is for the case n equals 0. This whole thing becomes 1, right? And then the integral becomes only the integral of f of t over one period, right? And in that case, we found that D0 is equal to what? Who remembers? D0 is equal to A, the amplitude of the signal, tau, the width of the pulse, divided by T naught, the period of your signal. Okay? Okay. Maybe in the example that we solved, we called it T. Same thing. Here we call it T naught. Okay? And for n not equal to 0, dn was equal to A over pi n multiplied by sine n omega naught tau over 2, right? So that was the coefficient of dn, right? And those coefficients, if I do the magnitude of dn in terms of a plot, right? Those coefficients are going to exist at which locations? The first one is going to exist at 0, right? So this is omega. So the first one is going to exist at 0. And that one will have a certain value, right? I don't care about the values now, but I care about the locations where they exist, okay? The second one, when n is equal to 1, is going to exist where? At omega naught. When n is equal to 1, then the location in frequency, this is location omega naught. And I will have some value, right? And when n is equal to 2, it will exist at 2 omega naught, right? And I will have some value. And then, as we mentioned last time, if you plot all of these, you will find somehow that they fall on this nice curve, right? You will find that the locations that you will get are going to fall somewhere on these ones, right? Now, this is a periodic signal with period T naught, okay? What if I make the period double? What do you think will happen? What's going to change? So, are these expressions going to change? Because they are general expressions in omega naught, which means they are general expressions in T naught, right? So what's going to change? What's going to change in this case? Any thoughts? If I change the period, if I make the period T naught bigger, what's going to change in this plot? Again, at n equals 1, I will have a value. At n equals 2, I will have a value. At n equals 3, I will have a value, right? But that value is falling at omega naught to omega naught. If I make T naught bigger, what will happen to omega naught? What's the relation between omega naught and T naught? Omega naught is equal to, so we know that omega naught is equal to 2 pi over T naught, right? So if I make T naught bigger, what happens to omega naught? Becomes smaller. What does it mean that omega naught becomes smaller? These two guys are going to be closer to each other, right? This and this, they will come closer to each other, right? They will become closer to each other, which means that the locations of those coefficients, right, are going to be more and more closer to each other. Now make T naught even further bigger, what will happen? So if I make T naught the double, for example, I will have coefficients at here as well as this one, right? And I will have another one here in between, right? Now if I make T naught 4 times, what will happen? I will have further coefficients in between, right? Because the omega naught, T omega naught, 3 omega naught becomes closer. And I will have coefficients at all multiples of omega naught, right? But what will happen is that the location of those coefficients, they will become closer. Now, how do I make this signal aperiodic? By taking T naught going to infinity. Because if I take T naught going to infinity, it means that those guys are pushed away, right? They are pushed away. I will not see them anymore. So the signal will not repeat. I will just have a square. And what do you think will happen in this case? those coefficients will become one right after the other, right? Such that the difference between them is going to be almost equal to 0. And if this is the case, if I have values, don't forget that these stems are just representing values, right? When I draw something with a stem diagram, it means that I have a value here, a value here, a value here, and so on. So those points, they will become close to each other such that they form, rather than being points, they form a continuous curve, right? So what will happen basically is that my discrete representation in frequency domain, which used to be discrete, in case of aperiodic, it will become continuous, right? Now, how do I get it? It's going to be something very similar to what I have here. Just think that you made t naught equal to infinity. So this means that this integral over one period is going to be an integral from minus infinity to infinity, right? And then the 1 over t naught will disappear for one reason or the other, because that's a mathematical derivation. I don't want to do it, right? And the n omega naught will become a continuous variable, which is given by omega, directly the continuous frequency, because we ended up with continuous function in frequency domain, right? So rather than being at n omega naught, which means at omega naught 2, omega naught 3, omega naught, they will become closer and closer and closer, such that this n omega naught will become omega, a continuous variable. Okay? So this means that eventually I will have an expression, right? So for the case of aperiodic, right, the frequency domain representation, right? So case of aperiodic means that t naught goes approximately to infinity, right? Then the frequency domain representation will move from discrete, it will become continuous, right? So as I take the period goes to infinity, which means that I make my time domain signal aperiodic, and this means that it becomes just this signal, right, which has a width equal to tau and nothing. So there is no repetition from all sides. That's it. I pushed everything away, so it became an aperiodic signal. Then in the frequency domain, so this is time domain, this is frequency domain, right? So in the frequency domain, what I will have is, instead of, so I push those, and instead of having the discrete, I will have a continuous diagram as a function of omega, right? And instead of calling this dn, I will call this f of omega, right? I will call this the frequency domain representation of my time domain signal f, which was aperiodic. And in this case, its frequency domain representation is no longer discrete. It becomes a continuous function, right? Which is tightly related to the discrete one. It's actually, you remember that dotted location that I told you that they will fall on? It will become, that dotted location will become the continuous function, okay? So basically, that's what happens. Now the expressions is f So if I have time domain signal, f of t, I call the frequency domain representation of that signal capital F of omega. So I'm no longer using dn or cn or an, right? Because I don't have n anymore. It becomes continuous. It's no longer integer discrete, right? It becomes a continuous, and in that case, I just capitalize the function name. So instead of small f, I call it capital F. And instead of being a variable of time or a function of time, it becomes a function of omega, which is the frequency, right? And it is a continuous function in general in frequency. And the relation is f of omega is equal to the integral from minus infinity to infinity, f of t, your time domain signal, multiplied by e to the minus j omega t, and you integrate with respect to time. So once you finish this integral, the time variable will disappear because you have substituted it, right, by the integral, and you will end up with a function only of omega, right? Now what if I have the frequency domain representation and I want to get the time domain representation? Remember, in the Fourier series expansion, it used to be a summation. Why? Because the frequency domain representation was discrete. Now it is continuous. So the inverse relation, the relation that takes you from frequency back to time, is going to change from summation. It will become again an integral. And the relation in that case is that f of t is equal to 1 over 2 pi, right? The integral from minus infinity to infinity, f of omega, the frequency domain representation, multiplied by e to the j omega t, but this time you integrate with respect to frequency, such that you get the result as a function of time. And notice that there is a difference between going from time to frequency, the first equation, and going from frequency to time, the second equation, and the difference is in two things. In one case we use a minus sign, right? While in the other case it's a plus sign, okay? Also, there is no scaling factor here, while there is a scaling factor in the inverse relation. So this relation, the first one, is called the Fourier transform. So instead of saying Fourier series, it becomes a Fourier transform, right? And the second relation is called the inverse Fourier transform. So I go back from frequency to time. So we call it the inverse Fourier transform, which is the relation that takes you from frequency back to time, okay? While the first one that takes you from time to frequency is called the Fourier transform relation, okay? So that's the topic that we started today, the Fourier transform. Let's apply this Fourier transform on some functions and see how we can solve, okay? So let's take an example or two in the remaining time. Any questions so far about moving from aperiodic signals to periodic signals? Clear? And the logic behind that move, and kind of where the equations come from, but we did not do like a rigorous mathematical derivation, and we don't need to do it. It just tells you why the equations look so. Now, keeping this in mind, still, when I take the Fourier transform of a signal, what do I represent? I still represent how much of the signal exists at each frequency value, right? But instead, for the case of periodic, instead of doing this at certain discrete frequencies, and the signal does not have any components on other frequencies, right? Only at the discrete ones, omega naught to omega naught, 3 omega naught, and so on. In the case of the aperiodic signal, I have values for the signal at a continuum, at a spectrum of frequencies, right? That's why in the frequency domain, it looks like a continuous function instead of being discrete values, okay? So that's the only thing. But the meaning is still the same. The physical meaning is still the same. I'm looking at the same signal from a different perspective, which is focusing on how much value the signal has at a particular frequency, as opposed to the time domain, how much value at a particular time, right? So it's still the exact same concept, okay? Let's take a couple of examples. We can start actually by this, or let's leave that to the end. Let's start by the famous e to the minus, so assume that f of t, so example 1. Okay. So assume that f of t is equal to e to the minus at multiplied by unit step of t. Okay. Find the Fourier series transform, right? So sorry, Fourier transform. Right? It can be written as find the Fourier transform of f of t, okay? Or I can write this to you as, instead of saying this, I will say you find capital F of omega, or sometimes they do this, f of t. So all of these are the same thing. This last one reads the Fourier transform of f of t. The middle one reads the frequency domain representation of f of t, or f of omega directly, okay? And the first one reads the Fourier transform of f of t, but written in words, okay? So all of these are the same thing, okay? So now we need to find that Fourier transform. What should we do? What's the only tool that we have right now to do that? The definition, right? So again, for the solution of this, using the definition, right? What does the definition say? It says that f, what does the definition say? It says that f of omega is equal to integration from minus infinity to infinity, f of t multiplied by e to the minus j omega t, and I integrate with respect to time or frequency? Time. So I integrate with respect to t, right? So apply this. So basically f of omega, I will substitute f of t with this expression. So it's equal to the integral from minus infinity to infinity, e to the minus at multiplied by unit step of t, and I multiply this by e to the minus j omega t, and then the integral is with respect to time, right? Now, with the existence of the unit step, I know that this is going to be equal to 0 for t less than 0, right? Because it's a function multiplied by unit step, right? So this means that I can change the integral to be from 0 to infinity, right? And in that case, from 0 to infinity, the unit step becomes equal to 1, so it will disappear, and it is e to the minus at multiplied by e to the minus j omega t dt. What's the solution for this integral? Combine the exponentials, right? So you'll end up with what? The integral from 0 to infinity, e to the minus, بعدين a plus j omega, and then multiplied by t, and you integrate with respect to time, right? So this is equal to what? Same thing. So we have e to the minus a plus j omega t, and over, yeah, a plus j omega, and there is a minus sign, right? And then the upper limit, infinity, and the lower limit, 0. Okay? So what's going to be the result? So when you substitute t equals infinity, this would be equal to 0, right? When you substitute time, don't forget that we are substituting for time, right? So when you substitute time goes to infinity, this exponential is going to go to 0, okay? And when you substitute time equals to 0, this exponential goes to 1. So basically 0 minus 1 over AJ omega. So it's equal to 1 over A plus J omega, right? There is one missing piece. What's the missing piece? That's the result, right? But there is one missing piece. You cannot write it this way and just stay silent. There is one missing piece. What's the missing piece? Huh? لا ما خلاص ما unit step احنا we substituted it. We ended up changing the limits of the integral. No, the steps we did is okay, but I cannot write the answer like this and stay silent. There is one missing part. No. Yeah, and you are close, but it's not as you said it. Fine. This exponential has two parts, right? There is a real part and there is an imaginary part. Okay? Imaginary part corresponds to a sinusoidal function, so I don't care about it, right? Even if I go to infinity, it's a bounded function, right? What about the real part? I have e to the minus at and then I substituted infinity. What if a was negative? What would have happened here? The e to the minus infinity will become to the e to the infinity, which means that this whole thing will blow out, right? So I cannot say that this is equal to this except if I put a condition that a must be greater than 0, right? If a is negative, I cannot solve this integral, and the Fourier series, the Fourier transform does not exist. Okay? So again, we didn't say at the start that a is a positive or a negative number, right? We just said a as a constant, right? So you have, when you deal with this mathematically, you have to be careful that you cannot simply say when I substitute infinity, this is going to go to 0. It's not true if a was negative. It will not go to 0. It will blow out, right? So you cannot do that. You have to say that this is solvable or this is equal to 1 over a plus j omega under the condition that a is greater than 0. What if a is not greater than 0? This signal does not have a Fourier transform. So the condition, based on that, so we solved an example and we will extract also an important property from that example. So from the previous example, we can generalize that not all time domain signals will have a Fourier transform. Okay? So the condition for f of omega to exist, similar to the condition that we had for the Fourier series, the one that we did in the last lecture, okay? The condition for the Fourier transform to exist is very similarly, you can find out that this condition is the integral from minus infinity to infinity of your time domain signal, absolute value, is bounded. That integral does not go to infinity. If that integral goes to infinity, your time domain signal cannot be converted into frequency domain using the Fourier transform. You might have some other methods, but using the Fourier transform definition, you cannot get a frequency domain representation or an f of omega for that signal unless this condition is true. Okay? So this condition is necessary to find, and that applied to the example that we did before. That was the condition that a must be greater than 0. It must be a positive number. Okay? Let's take a very trivial example, but will show me whether you are studying the previous part or not. So let's say example 2, and f of t is equal to the delta function. So I have a delta in time, and I want to get its Fourier transform. Okay? So what's f of omega in this case? Okay? Anyone can solve this? So again, using the definition. What's the definition? f of omega is equal to the integral from minus infinity to infinity, f of t multiplied by e to the minus j omega t, and I integrate with respect to time. So this is going to be equal to the integral from minus infinity to infinity. F of t is delta, so it will become delta of t, the impulse function, right? Multiplied by e to the minus j omega t, and I integrate with respect to time. And then, what's going to be the result? So, how do you solve this? Why 1?
Because for the sampling property says that for t is equal to 0.
Exactly. So basically, this is, you remember the sampling property of the delta function? This is the delta function multiplied by some other function, the e to the j omega t, and I'm integrating. So this integral is equal to this other function at the value of t equals 0, right? So when I take e to the minus j omega t and I set t equal to 0, I will get a value equal to 1. So the solution is 1. So very nice, right? That if in time domain, so if in time domain I have an impulse delta of t, right, as a function of time, then in frequency domain, this immediately corresponds to a constant equal to 1. And that constant exists at all frequencies, right? The signal is equal to 1 in frequency domain at all omega values, right? Why this is the case? Just from a physical interpretation, and then we'll stop there. Why does this make sense?
Because it's an impulse.
Okay, so impulse means something that varies very, 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 very quickly, right? It just happens and disappears in 0 time, which means that it will have components at all frequencies because it spans a very large frequency, right? So that's why an impulse in time domain corresponds to a constant signal that spans all possible frequencies in frequency domain. Because an impulse, if you think of it physically, it's something that changes in no time, which means that how much frequency it contains? It contains infinite frequency, right? So that means that when you look at it from the frequency domain perspective, it should span all the frequencies. It has all kinds of frequencies that you can think of, okay? So I will stop here. Next time we'll have some more examples, inshallah, after the quiz, yes.